I prepared a little script here, just the first part, which is some imports you need to do, which the language needs if you want to use certain models. And then I have an input folder that contains the input data that you need for water yield. The global water yield is composed, that we will see, is composed of 4 models. The first is you calculate on your basin the runoff. After that, or in parallel, you calculate the evapotranspiration on your basin. With those information, you need to calculate what happens with infiltration. So there is a module for infiltration. And finally, you can calculate your base flow. So in the end, you have on the whole basin, but usually you're interested in the closing in the outlet of your basin. In the outlet, you could have the information of the base flow and the runoff. So with these 2 information, you get the information of the discharge, which is basically what we want to understand. So these are the inputs you need. And the first module we're going to use is SCS. So how do I know if it's the first time I look into this, what kind of syntax to use? Because that's the problem with most of the tools. If there's not a lot of documentation, it's very difficult to start with it. And luckily, the spatial toolbox actually is this thing here. And a normal user would simply use the models from here. But if you want to chain them, you have to use the console. And that's what we're going to do now, because it makes more sense for us to create a chain and check the intermediate results. So we can look for run off here, and we will find a module that's called SCS runoff. We see that it has a couple of inputs, it has an output. What we can do here to get some help is we can say, we create a new, it's called SCS runoff. And that's how you build a model. You build this little model, and you have 2 helping methods. One is really help. You cry for help, and just to make sure that you run the model, which is this button here, or you run the script, which is this button here, or Ctrl+R, and it will give you a little description and stuff. So the module is experimental. The authors are the k.LAB team. And usually if somebody writes team, it's because it's not documented well, so nobody will know who did this. And you have description of the input parameters. This helps, but is not really what we need, because what we need is a template. And if you run this, you can just select it and copy and paste it in here. And this makes it easy to just say, okay, rainfall. We have an input map here. It's my rain. This is just the input folder, and I just attached the name of the file. I should just to show you, this is my folder. I have this input files, and then I have an output, which is currently empty. So I can just say input is rain. The in network is my stream presence. It's where I have network and where not. The map of curve number, CN, I named it CN. Number of events is events. And then there is my output. The output discharge is something new. So I can say it's my runoff, and it stays in the out folder plus, let's call it runoff.tiff, because it's a raster with the value of runoff in every cell, clearly. So out folder, this should work. And once I set all my inputs and outputs, I can call process, which will just launch the model. If I run this, it will do some stuff, and I can check, sorry, here, it generated a new map. what you would do is you would load it into your GIS and then check if the data are right and this kind of stuff. But while you do modeling and you prepare your little script to also do some digging of information if the results of the model are not right, because think this as a moment where you are writing a new model. Well, you can do something here, like there is a class that allows you to read the raster file, let's say the runoff, and just it gets a format. It checks on the format if it's a TIFF, an arc grid, or whatever, and it returns you a layer. And with this layer, we can then create a little map object that can have a width, if you want, width of 1200 and a height of 1000. And then I just add my layer there, and this would be layer. And then I can say, oh, display my map. And if I run this now, it will show me the map without, it's not visible, but in here you have a projection, and if you overlay other kind of data, you can also check if the result is actually geographically correct. This is also something I would use. Sometimes in k.LAB we have issues with projections, so it might be a good idea to first, before you run to someone and say it's not working, k.LAB, you can check this and overlay your data here. If there is a shift here, since it uses the exact same libraries, geographic libraries as k.LAB, there might be an issue. Base flow, water volume, perfect. And here it takes as input the infiltration we just generated, the net infiltration, the network, map of flow direction, and then it can produce several outputs. Again, here some are necessary and some not. The base flow is actually that thing that we wanted to calculate. So let's create a base flow output map. Base flow. And let's also plot the base flow in blues. Okay, this kind of makes sense. If you're into hydrology geomorphology, this kind of looks like a total contributing area map as any map that propagates stuff from the basin to the outlet, from all the parts of the basin to the outlet. In these kind of maps, it makes sense often to use a logarithmic visualization, because when you accumulate, the outlet value is very high and you have very low values in the source cells. How this actually integrates inside of k.LAB, because one thing we agreed on when we started to working on these modules was that the actual logic of the single knowledge of infiltrated water volume, of the runoff calculation, of whatever is necessary would be inside the HortonMachine. But then it should be used from k.LAB. And some of you saw this already yesterday. So this is the water yield model in k.LAB. And I think maybe Ferdinando can give you the point of view from the side of k.LAB, because
the interesting thing about this is that you saw, I mean, Andrea that did all the groundwork, and it has a process and it has a broken down the problem into its components, its logical components. So in order to do water yield this way, which is a simple way to do it, but it can be done all over the world, and it's the way that Invest, for those who know what it is, does it. Normally when you want to do this kind of modeling, you have to start like he did, putting together data, creating files, all in the same projections, all in the same grid size, etc., putting them into a directory, writing the places where they are, etc., etc. And it is great because in the end, that's what you need to do if you follow the process technically in the engineering way of running a model. You know the model, you give it an input, you get the outputs, you use the outputs. It's all totally fine. k.LAB is meant to skip those parts and just use semantics and artificial intelligence so that the work of the modeler that he showed you, and it's important to know how to do that, can be done by a machine, by just mentioning, by just using the concepts that actually mention and describe the problem that you want to solve. So this is the example of how we write the semantic annotations, as we call it, for the models that you just saw. So the models you just saw are here. Basically, when I say using here, this basically points back to the HortonMachine. And we are using a lot of the models of the HortonMachine. By the way, we're not using all of them, and it's a pity because there is a lot of stuff we can use, and we should discuss how to use the entirety of it. Because at this point, the two projects are kind of, brother projects. So it's really good to see that one uses all the possible elements of the other. But what you see over here is a completely different kind of code. This is the language that we use for k.LAB, which is called KIM. It's knowledge integrated modeling, which is models integrated by knowledge. And basically everything you see here is knowledge, is concepts, which refer to known ontologies, basically to documents that describe each of these concepts, so that you can, for example, color code. Model evapotranspiration, which is red because it's a process. Within hydrologically corrected watershed, this is the most important thing. Those models need to run in a watershed. If they don't run in a properly delineated watershed, they produce only a mess because the model cannot assess where each drop of water falls, because it will fall out of the boundaries of the map that you're using. So if you do it on a rectangular region or on a country, which is composed by several watersheds, but they don't cover the country exactly, they may go outside, etc. A decision maker needs to know all these details, so they cannot do it directly. Why? By just saying that evapotranspiration is a process that we need to compute within a watershed, and a particular kind of watershed, because it needs a bit of a correction in order to work properly. Here, we just attach a model to this part, to the watershed, so that when we ask for evapotranspiration, the program automatically knows that it needs to build a coverage of watersheds, and within each of the watersheds, which is the operator within, which is a logical operator, just stating the problem and nothing else, not saying anything about the how, it knows that it needs to distribute this model through watersheds. And when that is done, if the person who is actually asking for this result has asked for this result in a country, the system will, by virtue of this definition, take all the watersheds in the country, run the model in every watershed, and then merge the results and cut them up so that they reflect the country. And this is all done automatically. And that's the point of k.LAB. It makes it simple for scientists, for non-scientists to actually ask scientific questions. But it also makes it very simple for scientists that are different scientists to ask questions about a science that is not their science. And that's why it's an integrated modeling program. So if I am a social scientist, I know exactly how to compute certain social things, but I know nothing about how to compute water pollution. And water pollution needs to compute water transport, and for water transport, you need hydrology. So if you can ask questions logically, like in these models here, then you can integrate models because you don't have to worry about the details of the how, you just worry about the what. And each person who knows about the what of a particular problem can put something like this online, so that a machine can find, the same way that you find something in Google, you look for, you want to buy a car and you look for cars in Google and you get a description and where to buy them and how much they cost. Here you need to know about potential evapotranspiration, and you type here potential evapotranspiration, you know nothing about it. The system goes on the network, finds these models and computes it for you, and then it will go back to your model, which knows how to compute these things using this as an input. And that's the spirit. So if you look at these models, each model is very short, because first of all, it doesn't worry about the technical details. That technical details, you just saw it happening from there, but you state your outputs. So this is the model of evapotranspiration that also produced the evapotranspired water volume, which is a different color. This is a process. This is a quality, something that you can measure. So evapotranspiration creates a volume of water which is evapotranspired, and that's your likely result of interest. And in order to compute that, which is basically the semantics for the inputs that are needed, the stuff that Andrea was putting file names for, here, instead of file names, you just state what you want logically. So I need the maximum atmospheric temperature in Celsius. I need the crop coefficient, which is another concept. I need the atmospheric temperature, which is not either the maximum or the minimum, and it's not the average of the two, so it's an independent input. You need the solar radiation. I want it in megajoules per cubic meters per day, and you say nothing else. You don't say about where to find it. You don't say anything about where to find the files or how to measure it, etc. You just say that you want this, and this will go online and find whatever it needs to do. So for each of the modules of the HortonMachine that compute water yield, and it's just a small part of the HortonMachine, and this is a very small part of areas, you see that there is a model here, that Baseflow, PetCalc, etc. Each of those things are connected, but also independent. So you can compute each one of these. And if you want to not compute the model, not know anything about the model, you go on the Explorer, which has a query bar. But as you can see here, these are the outputs of the HortonMachine. This is k.LAB, but the outputs that the HortonMachine is printing, would be printing in the console over there. It's now capturing them and printing them as outputs of k.LAB. And it's basically the same way that we integrated the HortonMachine. We integrate a lot of other software that is offline. We don't always have the fortune of being able to work directly with the providers and the developers.
I'm happy that we were able to just show also this part. And well, so what is the message for all you modelers out there? Come over and bring your models into k.LAB, because it's really a fun place to have them run. And as he said before, I think for somebody that writes a model, having it run in your own cellar is not that much of fun. If you have it somewhere where really many people can use it, that's one cool thing. But even more if somebody else from another science uses it. That, in my opinion, that was the idea when we started all this. So I'm happy that after only 20 years, I've been able to find a place where this actually works. So thank you. Thank you for having me today also.